there are a lot of really great problems that you can do regarding a person in an elevator. So the first question that I have is, here's a man in this elevator, and the mass of the man is 65 kilograms. If this elevator is stationary, then what is going to, see he's standing on a scale right here. What's the bathroom scale going to read? What's the scale reading? Okay, so to think about that, first we need to draw just a free body diagram. Here's my man. The downward force on the man by the earth. And then we have the upward force on the man by the scale. Okay, so if this is stationary, then we're in equilibrium, so the up force has to equal the downward force. And so if the force on the man by the earth, or the force of gravity, is just the mass times the gravitational field strength, then that means I have 65 kilograms times 10 meters per second squared gives me a force of gravity of 650 newtons, which gives me a normal force, or a scale reading. The normal force will be the reading on the scale of 650 newtons. How is this going to change then? How is this going to change if I have the man in the elevator and it's traveling upwards at a velocity of 4 meters per second? So here I have the man in the elevator traveling up at a velocity of 4 meters per second. Think about, is the elevator accelerating? And if your answer is no, then I'm in equilibrium, meaning the net force, or the sum of the forces, or the total force, all of the forces, is equal to 0 newtons. So this is no different than the stationary situation here. So the scale reading will still read 650 newtons. Okay, same person, same elevator, but now the elevator is traveling upwards. The elevator is traveling upwards, and it's speeding up at a rate of 2 meters per second squared. And what will the scale reading be now? What will the scale reading be now? And just like any other thing, I like to think of this as if I'm going up and I'm speeding up, my acceleration is also going to be upwards. That means that my net force, the total force, the sum of the forces, is going to be in the upward direction. So when I draw my free body diagram of this man, I'm going to draw it right here. The forces on the man, this force of gravity doesn't change from here to here to here. This force of gravity is always going to be the same, because that's the guy's weight. His weight does not change. It's going to be the normal force, or the support force, that changes. That's what gives us the difference in the scale reading. And so if the net force is upward, then that means that the normal force, the upward force, the force on the man by the scale, needs to be bigger. I'm just going to call it the normal force this time. All right, so then what does the scale read? How do we find that value? You have to take the sum of the forces in the y direction. That's going to be the normal force minus the force of gravity. And the sum of the forces in the y direction is going to be the mass times the acceleration, which is the normal force minus, and I'm just going to go ahead and plug in mg here. So our normal force, or the scale reading, is going to be the mass times acceleration plus the mass times the gravitational field strength, or the guy's mass times acceleration plus g. We can plug in some numbers here if you want. So the mass of 65 kilograms, the acceleration of 2 meters per second squared, plus 10 meters per second squared. And it didn't matter if you plugged your numbers in here or down here. I always wait until the last minute because sometimes they might just ask for this without any numbers. So then this would be your answer. All right. So 65 times 12 is 780 newtons is going to be our normal force, or the force of the scale reading. Which makes sense because if this object is accelerating, it's going upward, that the elevator is going to push upward on the person. It's the part that's moving, and so the scale is going to get bigger. The reading is going to get bigger if you're pushing upward and accelerating upward. All right, how would this change then if instead of accelerating upward, going upward and speeding up, maybe we are traveling downward and slowing down. So here we are, same guy, traveling downward and slowing down. So if I'm traveling downward, this is the direction that my velocity is in, downward. And if I'm slowing down, that means I'm traveling downward and I'm slowing down. That means my acceleration is going to be in the upward direction. So if my acceleration is upward, then my net force is going to be upward. Acceleration is upward, then the net force is also going to be upward. Now, this idea of the net force being upward, remember the free body diagram, if the force of gravity doesn't change, force of gravity is downward, right? If the net force is upward, that means the up force needs to be bigger than the down force, and so the normal force is going to be greater than the force of gravity, or the scale reading is going to be greater than if he's just stationary. If this acceleration, if it is, again, 2 meters per second squared, then the math looks no different than it did earlier. So this situation here is going to look no different than the situation where I am traveling downwards and slowing down. If the acceleration is upward, the net force is upward. We get the same math for this situation because the free body diagrams look the same. How is this going to change though? If we are, let's say, traveling up and slowing down. Okay. So if I'm traveling up and I am slowing down, then that means my velocity is upwards. I'm slowing down, so my acceleration is in the opposite direction. My acceleration will be downwards, which means my net force will also be downwards. So the force of gravity does not change. It's always going to be the same in this situation. So the force of gravity is still going to be equal to 650 newtons. We can go ahead and put that in first if we want to. Then if the net force is downward, that means the down force has to be bigger than the up force. So this upward force, the normal force, the force that tells us the scale reading will be smaller than the force of gravity. All right, so what does the math look like then? Well, same deal. We sum the forces in the y direction and we get the normal force and the force of gravity. I'm going to have the sum of I'm going to have the acceleration downward be in the positive direction. I like my whatever direction I'm accelerating in be positive, which would give me a negative normal force and a positive force of gravity. So I sum the forces in the y direction. That gives me the mass times the acceleration is, I'm going to flip these, mass times gravitational field strength minus the normal force. Pull this over to the other side. Mass times acceleration minus mass times gravity is the normal force, negative, so we'll pull that through. And so here we get mg minus a equals the normal force. We could plug these in if we were saying the acceleration is 2 meters per second squared. Then that gives us 10 meters per second squared minus 2 meters per second squared times 65 kilograms. This will give us our normal force, which will be less than the force of gravity at 520 newtons, if I did my math right. So the key takeaway with any problem involving elevators or things that are accelerating upwards or downwards, think, which direction is this accelerating in? Once you know which direction it's accelerating in, then you know that is the direction of the net force. If the force of gravity never changes, then it's the normal force or the upward force that needs to change. This would be the exact same problems and logic if I had like a rock tied to a string. Here's my string that the rock's tied to. Same idea if I were to pull up on this rock. If I were to pull up on it and accelerate it upwards, then we could talk about the force of gravity of the rock and the force of tension. So an elevator is just an idea of a problem. You see this, this example in a lot of different situations.